All right, so continuing with looking at products of vectors. Last time we were focusing on a scalar product, which is rather simple. It's a product of two vectors that leads to a scalar value. And I say it's rather simple because it's rather simple to calculate compared to a vector product, which is a product of two vectors which leads to another vector. And it leads to a vector that is always orthogonal or perpendicular to the two vectors we're looking at, either going up or down from those vectors, if we imagine those vectors being on the horizontal. That said, there's a lot of good stuff here. Let's just kind of get straight to calculating the vector product. So I want to find a vector of length 2 that is perpendicular to these two vectors here. So first I need to find the vector product, because the vector product is always a vector that is perpendicular to these two. And so the vector product we show with our cross for a times, not the dot for the dot product. And the way we find it with three elements is like this, which this is in your IB data booklet, but in general, it's not nearly as quick as finding the scalar product. But for example, the first element is this times this minus this times this. The second element right here is this times this minus this times this. And with a bit of practice, it gets a lot more intuitive, although again, you don't need to memorize this. So let's do it. Of the three elements, the first element that's going to go here is going to be 1 times 1 minus 3 times negative 2. So that's 1 minus negative 6, or 1 plus 6. The next element is going to be 3 times 2, which is 6, minus negative 2 times 1. So that's the same as 6 plus 2. And then the last element, which goes here, will be this times this, which is 4, minus this times this, which is 2. So 4 minus 2. Easy to get some things mixed up. Definitely got to be careful with your negatives. So in the end, the vector product of these two is 7, 8, has elements 7, 8, and 2. And so that vector is perpendicular to both A and B, and we call that the vector product. All right, I want to find a vector, though, that is perpendicular to A and B, but has a length of 2. So if I look at this vector product right now, if I find the magnitude of A times B, it's probably not going to be 2. Magnitude is pretty straightforward, though. It's the square root of 7 squared plus 8 squared plus 2 squared, which in this case is root 117. Yep, not 2. And so how do I find a vector length that is exactly 2, but is still perpendicular to these? Well, I just need to take this vector here, and I need to scale it down so its length is not as much. And we did this in similar questions before, where first we want to find the unit vector. And so if I take that vector of 7, 8, 2, if I multiply it by 1 over root 117, that is now the unit vector. This is the unit vector of A times B. And so this here has a magnitude of exactly 1, or a length of 1. I want a length of 2, so I just need to double that. So I take this, and instead of 1 over that, I'll have it as 2 over that. And there's my answer. I can leave it like that. And so keep in mind that last part just builds upon ideas we saw before in previous lessons about taking a vector, and if we need to scale it to a particular length, we first generally go back to the unit length and then multiply that by some value. All right, before I move on, I will say the magnitude of a vector product, which in this case was root 117, also relates to the area of the parallelogram formed by these two vectors. So let's say A looks like this and B looks like this. Well, if I make a parallelogram out of that, the area of this parallelogram will be exactly root 117, which is a nice sort of geometric relationship to deal with these vector products. And that's what we want to use for this question here. We have two vectors in this sort of ijk component form. But I know the area of the two vectors, if you form a parallelogram out of it, is exactly 4. So first of all, though, first thing I would like to do is make a little visual here. So I have, again, I'll grab a ruler here. I have vector A. Let's say vector A looks something like this. Let's say vector B looks something like this. I'm not too worried about making this too, at the scale or anything. And so the idea is, if I imagine creating a parallelogram out of this, the area of this parallelogram is the same as the cross product of these two, or the vector product of these two vectors, which we know is exactly 4. So all of this is 4 square units. And so if I look at the vectors here for A, I'm going to write this A as a column vector. So I have, I don't know how many i's, but I have, so x, 1 and -1, and vector B is 1, 1, 2. And I want to multiply these two together. And so the vector product of A times B will be like before. I have to first go 1 times 2 minus -1 times 2. So that I get 2 plus 1, or 2 minus -1. And then I continue with the rest. My highlight is going to get messy. So next, for the next element right here, I want to go -1 times 1 minus x times 2. So it's -1 minus 2x. And then my last elements will come from, will be, where am I looking at here? Again, it'll be x times 1 minus 1 times 1. So x minus 1. Which I can clean that up a little bit and get just 3. -1 minus 2x and x minus 1. Those are my 3 elements. And I know that's my vector product. Well, I know the absolute value of that. For example, if I take the absolute value of this, or the magnitude of this, I know that's going to equal 4. So I want to find the magnitude of this cross product. And so if I find the magnitude of A times B, I want to find the square root of 3 squared plus -1 minus 2x squared plus x minus 1 all squared. And keep in mind, I know all that equals 4, which means everything here must equal 16, because the square root of all this equals 4. And so I can clean this up slightly, although I'm going to go to my GDC pretty soon, but if I clean this up a little bit, I do get 9 plus 1 plus, I'm just going to expand these binomial squares here. So 1 plus 4x plus 4x squared plus x squared minus 2x plus 1. All that is just slightly cleaned up from this. Equals 4. If I come that far, I might as well equals 16. The square root of that equals 4, but I can imagine squaring both sides. So it's a 16 that actually matters to me more. If I come this far, I might as well collect like terms. I get 5x squared plus 2x minus 5 equals 0. I'm going to solve this with a GDC. This doesn't factor anyways. So I'll solve. You can solve by graphing or something, or the quadratic formula. We get x equals approximately -1.2198 and approximately 0.8198. Well, notice up here, it does tell us right here that x must be, whatever x is a positive number. So I know in the end, I'm only looking at this. And so I can say, therefore, x is approximately, to 3 significant figures, 0.820. All right, lastly, I want to look at the idea of components of one vector in the direction of the other. So for example, if I have these two vectors, if I talk about the component of A in the direction of B, then I'm imagining kind of this having a right angle right here, where I'm looking at just this part here. This vector here is, we call the component of A, because it has to do with one of the directions of A, but in the direction of B. So that component, call that again, component of A in the direction of B. So how could we figure that out? Well, if we knew this angle here, we could imagine some fairly simple trigonometry in which the length of vector A, that's the magnitude of A. In fact, I'll just write it like this. The magnitude of A. And if I knew the magnitude of A and I knew this angle, then this component here would be, I could use a cosine function. And I could say the cosine of theta equals something over the magnitude of A. Or isolating for that distance, I can see that this part here would be the same as just the magnitude of A times the cosine of theta. All right, well, we can also look at another component, which is this one here, which we call the component of A, but perpendicular to B. And that's what that arrow is there. Again, it's still showing me one of the directions of A, but this time in a direction that's perpendicular to B. And so I can use the same idea of basic trigonometry, except this time I'll use the sine function. And this would end up being the magnitude of A times the sine of that angle. All right, so now I want to find those values. I want to find this and this for these two vectors given right here. And you may assume that we need to find the actual angle of theta. And we could definitely find the angle of theta. In previous lessons, we saw how we can find the angle between two vectors. We won't actually need to find that angle. And that's because if I just kind of go back to previous lessons, for example, the last lesson we saw this property. The cosine of theta is the same as the dot product of A and B divided by the product of their magnitudes. All right, that's from the last lesson. Well, notice if I notice this here and this here, there's a lot of similarity. If I want to find that component of A in the direction of B, I need the magnitude of A times the cosine of theta. Well, notice if I take this relationship here, if I multiply both sides by the magnitude of A, this cancels out, that cancels out. And what I have on the left-hand side is exactly what we're trying to figure out, the magnitude of A times the cosine of theta, and that will equal just the dot product of A times vector B divided by just the magnitude of B. And so that component that I've highlighted in yellow right here, I can figure out just with that. And notice if I look at the right-hand side of this equation, I don't actually need the angle theta. So let's figure this out. The dot product of A times B is relatively easy compared to the vector product. Again, it's this times this, plus this times this, plus this times this. We saw that in the last lesson, so I'll say that pretty quickly. You should get 2 plus -6 plus another -6. And the magnitude of any vector should be relatively quick, just the magnitude of that, which we should get root 17. And so I get -10 over root 17, and I'm done. That is the magnitude of A times the cosine of theta, which is the component of A in the direction of B. And notice I didn't actually need any angles. So I can do something similar to find the component of A perpendicular to B. And that goes back to this idea that didn't come up in a previous group problem, but I have right here. It goes back to the idea of the area of a parallelogram. I've already mentioned the area of a parallelogram is equivalent to the magnitude of the vector product. Well, if we combine that with some trigonometry from earlier in the course, I can see that's also equivalent to the magnitude of V times the magnitude of W times the sine of theta here. And so I'm going to take that equation there, and if I solve for sine, divide both sides by this, I get sine theta equals this over this. So let me write that down a little more neatly here. So sine of theta equals the magnitude of our cross product, or vector product, divided by the magnitude of A times the magnitude of B. And if I then, like before, if I multiply both sides by the magnitude of A, this cancels out, and everything we see right here is what we're trying to figure out right there. And so that means everything I see that remains on the right-hand side will be equivalent to the component of A perpendicular to B. And so if I want to figure this out, so I'll just say again this. So So the magnitude of A times the sine of theta, I'm not actually going to figure out the sine of theta, will be the same as my cross product. And so the cross product, the magnitude of my cross product. So the cross product of these, if I go through all the steps, I should get a vector that I need to give myself a little bit more space for, but I'll squish it in right here. It should have components -5, 8, and 7, but I want the magnitude of that divided by the magnitude of B, which I already found before was root 17. So now for my numerator, again, I want a scalar value. I want the square root of -5 squared plus 8 squared plus 7 squared, which altogether is root 138 divided by root 17. And if I decimalize this, I get about 2.85. And that there is my decimal approximation, or I could stick with a radical if I want to keep it exact. This here, 2.85 approximately, is the component of A perpendicular to B. And since I decimalized that, maybe I'll decimalize my previous one as well. The component of A in the direction of B is approximately -2.43. I'll have both decimalized as well. Keep in mind though, you could find the angle and you could, you should get the same answers, but this is definitely faster. And this relationship right here, which came from this relationship up in my notes, up here, relates back to this formula right here, which goes way back in the course. The area of any triangle is related to 1/2 times the length of 2 adjacent sides and the angle in between. And as always, these are things we look at in our group problems in class. I'm done.